US Physics Olympiad, year 2023, USAPHO, final round. This examination had two parts, as usual, Part A and Part B. Each part had 3 questions and lasts for 90 minutes. Problem A1. Circus act. In this problem we consider a small ball bouncing back and forth between 2 points. In all parts below, the acceleration of the gravity is g. Collisions are perfectly elastic, air resistance is negligible, and the impact points are at the same height. The diagrams are not drawn to scale. Question A. Consider a ball bouncing between 2 inclined planes, which each make an angle theta less than 90 degrees to the horizontal. The ball has speed v0 at the impact points, which are separated by a distance d. Question 1. The ball can bounce back and forth along the same path, as shown. For what values of theta is this position possible? For these values, what is v0? Question 2. The ball can also take one trajectory while traveling to the right and a separate trajectory when traveling back. Let phi not equal 0 be the angle between the paths at the impact points. For what value of theta and phi is this motion possible? For these values, what is v0? Question B. Now, suppose the ball bounces within a semispherical well of radius of curvature r. As in part A2, alternates between 2 distinct points which have flight times t1 and t2 not equal t1. Find all the possible values of r in terms of t1 and t2. Question C. Finally, suppose the well has a sinusoidal shape described by y as function of x equal negative L multiplied by sine 2x over L. The ball takes 2 distinct paths with the flight times t1 and t2 not equal t1, and the horizontal distance between the impact points is less than pi L. Find all of the possible values of L in terms of t1 and t2. Solution for question A. Consider a ball bouncing between 2 inclined planes, with each make an angle theta less than 90 degrees to the horizontal. The ball has speed v0 at the impact points, which are separated by a distance d. First, the ball can bounce back and forth along the same path, as shown. For what value of theta is the motion possible? For these values, what is v0? Solution. To go back and forth on the same path, the ball must impact the plane normally, which means that theta is the angle of its velocity to the vertical. The range of the ball is v0 square over g multiplied by sine 2 theta, which implies v0 equal square root from dg over sine 2 theta. That was solution for the first question from A. Solution for the second part from question A. The ball can also take one trajectory while traveling to the right and a separate trajectory when traveling back. Let phi not equal 0 be the angle between the paths at the impact points. For what values of theta and phi is this motion possible? For these values, what is v0? Solution. The two paths have the same initial speed and the same range, which means the initial angles of the velocity to the horizontal must be pi over 4 plus or minus phi over 2. Since the initial and final angles to the normal are equal in the collision, the angle of the planes to the horizontal must be theta equal 45 degrees. Given this, phi can take any value between 0 and 90 degrees. Considering the range yields d equal this expression, or v0 square over g multiplied by cosine phi, from which we find v0 equals square root from dg over cosine phi. As expected, this reduces to the answer above as phi going to 0 and becomes infinity as phi going to 90 degrees. That was solution for question A. Solution for question B. Now suppose the ball bounces within a semi-spherical well of radius of curvature r. As in part A2, it alternates between two distinct paths with a flight times t1 and t2 not equal t1. Find all of the possible values of r in terms of t1 and t2. Solution. From the previous question we know that the slope of the wall is theta equal pi over 4 at the collision points. So we have distance d equal r multiplied by square root from 2. X displacement with the time t1 is v0 multiplied by cosine pi over 4 minus phi over 2 multiplied by t1, which is equal to distance r by square root from 2. Y component of velocity in the upper point is 0. So we have v0 sine pi over 4 plus phi over 2 equal g multiplied by t2 over 2. Now transforms this formula to v0 cosine pi over 4 minus phi over 2 equal g over t2 over 2 equal g t2 over 2. We can divide this formula by this formula and finally get the radius r equal g t1 t2 over 2 square root from 2. This is the only possibility for radius, and that was solution for question B. Solution for question C. Finally, suppose the well has a sinusoidal shape described by y as a function of x equal negative L sine 2x over L. The ball takes two distinct paths with the flight times t1 and t2 not equal t1, and the horizontal distance between the impact points is less than pi L. Find all of the possible values of L in terms of t1 and t2. Solution. The slope of the wall is theta equal pi over 4 at collision points. So we have in one end first derivative equal negative 1 and on other end positive 1 on symmetrical wall. In the first case we have negative 2 cosine 2x over L equal negative 1, or cosine 2x over L equal 0.5. So here we have roots like this. X equal positive or negative pi L over 6. In the second case we have this equation, which leads to roots pi L over 3 or 2 pi L over 3. So we can show it on a graph like this. So on the same level of y as a function of x, we have two pairs of solutions, this one and this one, which corresponds to two pairs of points, x1, x2 and x1, x2. First case give us d1 equal 5 pi l over 6, and the second case give us pi l over 6, which corresponds to radius r 1, 2 equal d1, 2 over root 2 from question B. Using results from this question B, we have d equal g t1 t2 over 2, or finally L1 equal 3g t1 t2 over 5 pi, and L2 equal 3g t1 t2 over pi. That was solution for question C, and here we finished discussion for problem A1.